Today's lesson is a review of some math concepts that we're going to use a lot in physics. And specifically today we're going to look at algebra. Now, what I want to do is, to start things off, get you to just have a look at this expression right here. If I gave you this and told you to solve for x, you'd probably use something that a lot of my students call BEDMAS, or you might have heard of it as PEDMAS or PIMA or something along those lines. Basically what this is a mnemonic that refers to the order of operations. So in this expression here, we have some multiplication, we have an exponent, we have some addition, and I need to do those in a certain order. BEDMAS tells me what that order is. So as a quick review, the B in BEDMAS stands for brackets. The E stands for exponents. The D for division. M for multiplication. A for addition. And S for subtraction. So when I'm evaluating an expression like this, I'm first going to look for any brackets. After I've dealt with brackets, I'm going to do exponents. Then division and multiplication can actually be done in any order. Those are basically the same thing as each other. And same with addition and subtraction. I don't have to do addition before subtraction as long as I do both of them after I've done any of this stuff. So now let's have a look at this expression again. Okay, do I have any brackets in here? No, so I can move down the list. Are there any exponents? Yes, here's an exponent right here. So that's the first thing I'm going to have to deal with. And I'm going to rewrite the whole expression after having dealt with that exponent. So 3 squared is 9. So my whole expression now is 2 times 9 plus 1 equals x. Okay, brackets and exponents are done. The next thing I can do is any division or multiplication that appears. Here I have some multiplication. And I'll remind you guys, you might be used to seeing multiplication denoted with an x. You'll also see in this course sometimes just a dot can be used for multiplication, or if we simply have two things written beside each other, like two letters, that means multiplication too. So 2 times 9 is 18, and then if I write the rest of the expression, it looks like x equals 18 plus 1. And now that I've done my brackets, my exponents, my division and multiplication, I can get to any addition and subtraction that's left over, which is all I have. So I can do this 18 plus 1 now, which gives me x equals 19. So that seemed fairly straightforward. I was evaluating an expression to solve for x, and I had a bunch of mathematical operations to do, and I had to do them in a certain order. If we'd done this differently, if I'd maybe multiplied the 2 and the 3, and then got a result, and then squared it, I would have got a different answer. I would have got the wrong answer. So let's complicate things a little bit more. What if we did the same expression, but I took this x and this 3, and they swapped places? That's exactly what we have down here. So here's the 3 out front, and the x inside being squared. This changes things up a bit. Here, the x was all by itself. It was isolated. So all I had to do to solve for it was just evaluate this expression, just do this math over here. But what I'm going to need to do now, down here, is I can't just do my math to find x, because x is kind of stuck in the middle of a bunch of operations. X is not isolated. So what we're going to have to do is rearrange the equation to solve for x. Another word for this is we want to isolate x. The less fancy non-mathematical way of saying that we want to isolate x, is that we want to sort of undo all these mathematical operations that are happening around the x so that we can get x on one side of the equation all by itself. And that, like I said, is just another way of saying we're trying to isolate x. So the thing we're really trying to do here is, before I can go any further with this, I need to get x isolated. It's got all this math that's being done to it, and I want to undo that math. I want to sort of rescue x out of here, so it's all by itself like we had up here. In order to do that, the way I like to think of it is we need to know two things. We need to know SAM/DEB. No one ever actually uses this word. It's just BEDMAS, but backwards. And we need to know what we call the fundamental rule of algebra, which is we can do whatever we want to one side of an equation as long as we do the same thing to the other side. Okay, so we've got this expression. We're trying to isolate x, so undo all this math that's being done to it, which means we're going to have to do BEDMAS backwards. And whenever we do something to one side of the equation, we have to do the same to the other side. So let's try that. I'm going to just write BEDMAS out along the side here so I can refer to it again when I need it. Okay, so BEDMAS backwards. First thing I'm going to do is look for any addition or subtraction that's being done around the x. And indeed, after this x gets squared and multiplied here, it's going to get this 1 added to it. So that's the first thing I'm going to undo, because I'm doing BEDMAS backwards. So the problem I have is x has 1 being added to it. How do I fix that problem? Well, what's the opposite of adding 1? Subtracting 1. So I'm going to subtract 1 from this side of the equation, and I'm only allowed to do that if I subtract 1 from the other side of the equation as well. After doing that, that leaves me with 3 minus 1 on the left, and 2 times x squared on the right, because my plus 1 and my minus 1 will sort of cancel each other out. That was the whole point of subtracting 1 in the first place. Okay, so I've taken care of any addition and subtraction that was being done around the x. Next, I can look for any division or multiplication. And indeed, after this squared, this x gets multiplied by 2. I want to undo that. The opposite of multiplying by 2 is dividing by 2. So I need to do that to the whole side of the equation and to the whole side of the other side. Rewriting this, it gives me 3 minus 1 over 2 equals x squared, because these 2's will cancel out. Again, that was the whole point of dividing by 2. So finally, I can now look at any exponents or brackets I have to deal with. And my exponent here is the last thing. I want to undo that. So what's the opposite of squaring something? Well, it's square rooting something. So I'm going to square root this right-hand side of the equation, and I'm only allowed to do that if I do the same to the other side. At this point, I'll remind you that whenever we take the square root for the purpose of getting rid of a square, we have to remember that the answer can be plus or minus. Okay, so I think I'm pretty much done here. On this side of the equation, I am going to be left with the square root, plus or minus, of 3 minus 1 over 2 equals, and again, the whole point of doing the square root on this side was we knew it would cancel out with that squared over there, so I just have x over here. Now, to find what value x actually has, we can do the exact same thing we did way back up at the top, which is just do regular bedmass on these numbers. So there's sort of a two-part process here. We did bedmass backwards to undo this math around x and get x all by itself. And now we're going to do bedmass forwards on the numbers left on this side so we can figure out what exactly x is. So if I'm doing bedmass forwards, I'm going to do this 3 minus 1 first. Even though this is a subtraction, which is kind of at the end here, whenever we have a fraction like this, we imagine that there's brackets around the numerator and around the denominator. So that actually gets done first. So 3 minus 1 would be 2. 2 divided by 2 would be 1. So my final answer is plus or minus the square root of 1, which is just plus or minus 1. And we have solved for x. So the quick recap is, when we're trying to isolate a variable, or get it on one side all by itself, we try to undo all this math around it, which means we have to do bedmass backwards, until we've achieved that. And then, to actually evaluate it and solve for it, we need to do regular bedmass on the numbers left on the other side. Now, that's basically all the math we need to know for this lesson. And that should hopefully be a review for all of you. I won't say things are going to get harder, but they're going to seem harder. And the only difference is what we're going to do going forward is we're going to do this with more letters and less numbers. So here's a great example of what I mean. Here's an equation, just like we had on the last page. And we're going to solve for VI. Right away, this looks a little crazier because there's a lot of letters in here. But let me sort of break this down for you. So these letters down here that are sort of smaller and lower than everything else, those are called subscripts. Scripts meaning they're writing, and sub meaning they're lower. So they're literally lower writing. When you have some subscripts, they basically, I treat them and the letter before them as if they're all one big letter. So I don't treat this as v times a times v. I treat this as if it's a new letter I created called VAV. And I can't separate it out. It travels around as a block, as a chunk. So when we see some subscripts, you treat them as one letter with a letter before them. The other thing, actually, never mind. I won't mention that right now. We'll bring that in later. Over here on this fraction, I'll remind you about a point I just made on the previous page, which is that whenever we have a fraction written like this, we imagine that there are brackets around the top and around the bottom. So even though this is addition and this is division, this would get done first if we're doing regular bad maths because it's in these imaginary brackets. In case you're interested at all, VAV is average velocity, VF is final velocity, and VI is initial velocity. We don't need to know any of that to solve this problem. We just need to know that these are letters and we need to be able to move them around. But this is an equation from physics that we'll be using later on in this course. Okay, so I'm going to write BEDMAS down here because, again, we're going to be using it a lot. It's important. It'll be nice to refer back to it. So, the thing I'm trying to solve for here is VI. I'm going to underline it because that helps me remember what I'm trying to solve for and what math I have to undo. So, doing my BEDMAS backwards, I'm going to look for any addition and subtraction. So there's some addition going on here with the VI, but remember, this addition is inside brackets, so I can't get to it until I get all the way back up to B. So, there's no other addition and subtraction. There is some multiplication and division. VI is getting divided by 2. So I am going to undo that, multiply both sides by 2. This gives me 2 times VAV. Remember, if I just have two things written beside each other, it means they're being multiplied, even if I don't have that x in the middle. Equals VF plus VI. This times 2 and this divided by 2. Get rid of each other. So now, again, I've kind of got my imaginary brackets up here. It's up to you if you want to actually draw them or not. Now I've got so that the only thing left around my VI, the thing I'm looking for, is these brackets. So I can get in there and do those brackets, which means I can deal with this plus. So my VI, the only thing keeping it from being alone on one side of the equation by itself is VF is being added to it. To undo that, I'm going to subtract VF from both sides. And that gives me 2 times VAV minus VF equals VI. And we are done. So let's look at this next one here. Now remember, EK is not E times K, even though they're just two letters written beside each other. K is a subscript, meaning I treat it and everything immediately before it as if it's one letter. So I think of this as one symbol, one letter called EK. And then here we have 1/2 times M times V squared. Some of you might recognize this as the formula for kinetic energy, where that's kinetic energy, that's mass, and that is speed. So here what we're trying to do is we're trying to figure out what M is. And not only do we want to just solve for it like we did before, we want to actually get a value. get a number for it. So the first step is going to be to isolate it, like we did in the previous question. And then we're going to plug these numbers in for the other letters to get an actual value for it. So looking at this equation, here's the m that I'm interested in. Is there any addition and subtraction being done to it? No. Is there any multiplication or division? Well, yeah, there's a couple. It's getting multiplied by 1/2, and it's getting multiplied by v squared. So let's deal with these sort of one at a time. There's a few different ways to think about how to undo multiplication by 1/2. One way to think of it is I could, because here I'm multiplying by 1/2, I could undo that by dividing by 1/2. I can also think of it as when you multiply by 1/2, you basically cut something in half. So to get it back to where it was, you double it. In other words, you could multiply this side of the equation by 2. I find most students find that approach the most intuitive, so that's what I'm going to do. I'm going to multiply this side by 2, and the same to the other side. That's going to give me 2ek equals m v squared. This multiplication by 1/2 and a multiplication by 2 cancel each other out. So next, okay, is there any other multiplication and division with my m? Yeah, my m is being multiplied by v squared. So I want to undo that. I'm going to divide by v squared. That gives me 2ek over v squared equals m. So at this point, I've successfully isolated m. Now what I'm going to do is just plug numbers in here to figure out the value of m. And I'll just rewrite this equation up over here so you can see me do that. So here's the equation I just came up with down at the bottom. M equals 2 times ek divided by v squared. And now I'm going to plug in those numbers. What I generally do is whenever I'm substituting a number in for a symbol in an equation, I usually put it in brackets. So these brackets here represent ek. This is where ek was, but now I'm putting 500 in there instead. And then down here, I had something that was squared. This was v, but that's going to be 3 now. So now we're just doing, because my m is isolated, and all I have is numbers on this side, we're just doing regular bed maths. So I would go 2 times 500, because these are on the top of a fraction, so they're kind of in virtual brackets. And then I would divide that by, so the top would be 1,000, divide that by 3 squared, which would be 9. 1,000 divided by 9 gives me 111.1, repeating. In addition to doing calculations with numbers, like we were just doing, we can also do calculations with units. I sometimes think of it as this. So here's an equation. This is work equals force times distance. You don't need to know that for this lesson. That's just some bonus info. But what this equation means is if I want to know a number for work, I take a number for force, I put it in here, and I take a number for distance, and I put it in here. So a number here and a number here will give me a number for this. But I can do that same thing with units as well as with numbers. So if I want to know the units for force, or sorry, the units for work, right here, I can sub in the units for force and the units for distance. When I multiply those together, that'll give me the units for work. So the units of force are newtons. The units of distance are meters. So to get the units for work, I'm going to take newtons and multiply them by meters. And the way we often write that is just Nm, or often when we're doing units and we have two units multiplied by each other, we'll put that little dot in the middle. So Nm would be the units for work, and I would pronounce that Newton meters. A lot of times students are tempted to call this newtons per meter. They're just in the habit of saying per whenever they have two units that are combined, because that happens a lot, kilometers per hour being a great example. But remember, per means divided by. Newtons per meter would mean newtons divided by meters. That's not what we have here. Newtons times meters just gives me Newton meters. Let's do one more. So, here's an important equation in physics. F equals ma. F, you don't need to know what it is, but I'll tell you it's measured in units of newtons. And m, you don't need to know what it is, but I'll tell you it's measured in kilograms. We're trying to find the units of A. So this is the thing we're trying to find. Now here, the thing we're looking for is not isolated. It's not on one side all by itself. So that's the first thing I'm going to have to do. And I noticed that the thing preventing A from being isolated is that it's being multiplied by m. So I'm going to divide by m. Do it to both sides. And that gives me F over m equals A. So there I've isolated A, and now I want to know what units it has. I'll maybe just write this again over here. So here's my new rearranged equation. A equals F over m. And what I'm doing now is I'm going to substitute things in. So again, if I wanted to know a number for A, I'd sub in a number for F and a number for m. But because I want to know the units for A, I'm going to put in here the units for F and the units for m. F is in newtons, m is in kilograms. So the units of A are going to be newtons divided by kilograms, which we would sometimes write as, if we're doing units, rather than doing a fraction, sometimes we'll just do a slash. And this is pronounced newtons per kilogram. This one is per because we are dividing. And that is our algebra review.